The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we're going to talk a bit more about parallelism and about how you get performance out of parallel codes. And also we're going to take a little bit of a tour underneath the SoPlus runtime system so you can get an idea of what's going on underneath and why it is that when you code stuff, how it is that it gets mapped, scheduled on the processors. So when people talk about parallelism, one of the first things that often comes up is what's called Amdahl's Law. Okay, Gene Amdahl was the architect of the IBM 360 computer. He then left IBM and formed his own company that made competing machines. And he made the following observation about parallel computing. He said, and I'm paraphrasing here, if half your application is parallel and half is serial, you can't get more than a factor of 2 speed up no matter how many processors it runs on. Okay, so if you think about it, if it's half parallel and you manage to make that parallel part run in 0 time, still the serial part will be half of the time, and you only get a factor of 2 speed up. And you can generalize that to say if some fraction alpha can be run in parallel and the rest must be run serially, the speed up is at most 1 over 1 minus alpha. Okay? So it's pretty, this was used in the 1980s in particular to say why it was that parallel computing had no future. Because you simply weren't going to be able to get very much speed ups from parallel computing. You're going to spend extra hardware on the parallel parts of the system, and yet you might be limited in terms of how much parallelism there is in a particular application. And you wouldn't get very much speed up. You wouldn't get the bang for the buck, if you will. So things have changed today that make that not quite the same story. The first thing is that with multi-core computers, it is just it's pretty much just as inexpensive to produce a P processor right now, like 6 processor machine, as it is a 1 processor machine. So it's not like you're actually paying for those extra processing cores. They come for free, okay, because what else are you going to use that silicon for? And the other thing is that we've had a large growth of understanding of problems for which there's ample parallelism, okay, where that amount of time is in fact quite small. And the main place these things come from, it turns out, this analysis is kind of a throughput kind of analysis. Okay, it says, gee, only get 50% speed up for the application. But what most people care about in most interactive applications, at least for client-side programming, is response time. And for any problem that you have that has a response time that's too long and it's compute intensive, using parallelism to make it so that the response is much zippier is definitely worthwhile. Okay, and so this is true even for things like game programs. So in game programs, they don't have quite a response time problem. They have what's called a time box problem, where you have a certain amount of time, 13 milliseconds typically, because you need some slop to make sure that you can go from one frame to the next, but about 13 milliseconds to do a rendering of whatever the frame is that the game player is going to see on his computer, or her computer. And so so in that time, you want to do as much as you possibly can. And so there's a big opportunity there to take advantage of parallelism in order to do more, have more quality graphics, have better AI, have better physics, and all the other components that make up a game engine. Okay, so, but one of the issues with Amdahl's law, in addition, this analysis is a cogent analysis that Amdahl made, but one of the issues here is that it doesn't really say anything about how fast you can expect your application to run. In other words, this is a nice sort of thing, but you know, who really can decompose their application into the serial part and the part that can be, you know, can be parallel? Well, fortunately, there's been a lot of work in the theory of parallel systems to answer this question, and we're going to go over some of that really outstanding research that helps us understand what parallelism is. So we're going to talk a little bit about what parallelism is and come up with a very specific measure of parallelism, okay, to quantify parallelism. Okay? We're also going to talk a little bit about scheduling theory and how the SoPlus runtime system works. And then we're going to have a little chess lesson. Okay? So who here plays chess? Nobody plays chess anymore. Who plays Angry Birds? Okay. Okay. So, okay. So you don't have to know anything about chess to learn this chess lesson. That's okay. So we'll start out with what is parallelism. So let's recall first the basics of SoPlus. So here's the example of the lousy Fibonacci that everybody parallelizes because it's good didactically. We have the Silk spawn statement that says that the child can execute in parallel with the parent caller, and the sync that says don't go past this point until all your spawn children have returned. And that's a local sync. That's just a sync for that function. It's not a sync across the whole machine. So some of you who may have had experience with OpenMP barriers, for example, that's a sync across the whole machine. This is not. This is just a local sync for this function saying, when I sync, make sure all my children have returned before going past this point. And just remember also that Silk keywords grant permission for parallel execution. They don't command parallel execution. Okay? So we can always execute our code serially if we choose to. Yes?
Can the runtime system figure that spawning an extra child would be more expensive? Like, can it like look at the input and be like, oh,
we'll go into it. I'll show you how it works. Okay, later in the lecture. Okay, I'll show you how it works, and then we can talk about what knobs you have to tune. Okay? So, so it's helpful to have an execution model for something like this. And so we're going to look at an abstract execution model, which is basically asking, what does the instruction trace look like for this program? So normally, when you execute a program, you can imagine one instruction executing after the other. And if it's a serial program, all those instructions essentially form a long chain. Well, there's a similar thing for parallel computers, which is that, but instead of a chain, as you'll see, it gets bushier, and it's going to be a directed acyclic graph. So let's take a look at how we do this. So we'll do the example of fib of 4. Okay, so what we're going to do is start out here with a rectangle here that I want you to think about as sort of a function call activation record. So it's a record on a stack, and it's got variables associated with it. The only variable I'm going to keep track of is n, so that's what the 4 is there. Okay, so we're going to do fib of 4. So we've got in this activation frame, we have the variable 4. And now what I've done is I've color-coded the fib function here and into the parts that are all serial. So there's a serial part up to where it spawns. Then there's calling of the, recursively calling the fib. And then there's returning. So there's sort of 3 parts to this function, each of which is, in fact, a chain of serial instructions. I'm going to collapse those chains into a single circle here that I'm going to call a strand. Okay? Now, what we do is we execute the strand, which corresponds to executing the instructions and advancing the program counter up until the point we hit the fib of n minus 1. Okay? At that point, I basically call fib of n minus 1. So in this case, it's now going to be fib of 3. So that means that I create a child okay, and start executing in the child this prefix part of the function. However, unlike if I were doing an ordinary function call, I would make this call, and then this guy would just sit here and wait until this frame was done. But since it's a spawn, what happens is I'm actually going to continue executing in the parent and execute, in fact, the green part. Okay? So in this case, evaluating the arguments, etc. Okay? Then it's going to spawn here, but this guy, in fact, is going to do what it does when it gets to here is it evaluates n minus 2. It does a call, okay, of fib of n minus 2. So I've indicated that this was a called frame by showing it in a light color. Okay, so these are spawn, spawn, call. Meanwhile, this thing is going. So at this point, we now have 1, 2, 3 things that are operating in parallel at the same time. Okay, we keep going on. Okay, so this guy does a spawn and he has a continuation. This one does a call, but there's no. While he's doing a call, he's waiting for the return, so he doesn't start executing the successor. He's stalled at the silk sink here. Okay, and we keep executing. Okay. And so as you can see, what's happening is we're actually creating a directed acyclic graph of these strands. So here, basically, this guy was able to execute because both of the children that he had, one that he'd spawned and one that he'd called, have returned. And so this fellow, therefore, is able then to execute the return. Okay, so the addition of x plus y in particular, and then the return to the parent. And so what we end up with is, of all these serial chains of instructions that are represented by these strands, okay, all these circles, they're embedded in the call tree like you would have in an ordinary serial execution, right? You have a call tree that you execute up and down. And you walk it like a stack normally. Okay. Now, in fact, what we have is embedded in there is the parallel execution, okay, of which form a DAG, directed acyclic graph. Okay. So when you start thinking in parallel, you have to start thinking about the DAG as your execution model, not a chain of instructions. Okay. And the nice thing about this particular execution model we're going to be looking at is nowhere did I say how many processors we were running on. Okay, this is a processor oblivious model. It doesn't know how many processors you're running on. Okay, it just simply uses whatever, we simply, in the execution model, are thinking about abstractly what can run in parallel, not what actually does run in parallel in an execution. So any questions about this execution model? Okay. So, so just so that we have some terminology, so the parallel instruction stream is a DAG with vertices and edges. Okay. Each vertex is a strand, okay, which is a sequence of instructions not containing a call, spawn, sync, or return, or thrown exception, if you're doing exceptions. Okay, we're not going to really talk about exceptions much. They're supported in the software that we'll be using, but for most part, we're not going to have to worry about them. Okay, so there's an initial strand where you start and a final strand where you end. Okay, then each edge is a spawn or a call or a return or what's called a continue edge or a continuation edge. Okay, which goes from the parent when a parent spawns something to the next instruction after the spawn. Okay. So we can classify the edges in that fashion. And this is I've only explained this for spawn and sync. As you recall from last time, we also talked about Silk 4. It turns out Silk 4 is converted to spawns and syncs using a recursive divide and conquer approach. We'll talk about that on next time on Thursday. Okay? So we'll talk more about Silk 4 and what how it's implemented and the implications of how loop parallelism works. So at the fundamental level, the runtime system is only concerned about spawns and sinks. Now, given that we have a DAG, so I've taken away the call tree and just left the strands of a computation. It's actually not the same as the computation we saw before. We would like to understand, is this a good parallel program or not? Okay, based on if I understand the logical parallelism that I've exposed. So how much parallelism do you think is in here? Give me a number. How many processors does it make sense to run this on? 5? Okay, that's as parallel as it gets. Let's take a look. We're going to do an analysis. At the end of it, we'll know what the answer is. So for that, let's let TP be the execution time on P processors for this particular program. Okay? And it turns out that there are two measures that are really important. The first is called the work. Okay? So we're going to take, of course, we know that real machines have caches, et cetera. Let's forget all about just very simple algorithmic model where every strand, let's say, costs us unit time. Okay? As opposed to, in practice, they may be mini instructions and so forth. We can take that into account, but let's take that into account separately. So T1 is the work. It's the time if I had to execute it on one processor, I've got to do all the work that's in here. Okay? So what's the work of this particular computation? I think it's 18, right? Yeah, 18. Okay, so T1 is the work. So for even though I'm executing in parallel, I could execute it serially, and then T1 is the amount of work it would take me. Okay, the other measure is called the span, okay, and it's sometimes called critical path length or computational depth, and it corresponds to the longest path of dependencies in the DAG. Okay? We call it T infinity because even if you had an infinite number of processors, you still can't do this one until you finish that one. Can't do this one until you finish that one. Can't do this one until you finish that one, and so forth. So even with an infinite number of processors, I still wouldn't go faster than the span. So that's why we denote it by T infinity. Okay? So these are the two important measures. Now what we're really interested in is TP for given P. And as you'll see, we actually can get some bounds on the performance on P processors just by looking at the work, the span, and the number of processors we're executing on. So the first bound is the following. It's called the work law. The work law says that the time on P processors is at least the time on one processor divided by P. So why does that work law make sense? What's that saying? Sorry?
Like work is conserved, sort of? I mean, you have to do the same amount of work.
You have to do the same amount of work. So on every time step, you can get P pieces of work done. So if you're running for fewer than T1 over P steps, you've done less than T1 work over time TP. Okay? So you won't have done all the work if you run for less than this. So the time must be at least TP. Time TP must be at least T1 over P, because you only get to do P work on one step. Okay? Is that pretty clear? Okay, the second one should be even clearer. It's the span law. On P processors, you're not going to go faster than if you had an infinite number of processors, because the infinite processor one could always use fewer processors if it scheduled it. Okay, once again, this is a very simple model. We're not taking into account scheduling. We're not taking into account overheads or whatever. Just a simple conceptual model for understanding parallelism. Okay? So any question about these two laws? So these you should, if there's going to be a couple of formulas in this lecture today that you should write down and play with. Okay? So these two, they may seem simple, okay, but these are hugely important formulas. Okay? So you should know them. That TP is at least T1 over P, that's the work law, and that TP is at least T infinity. Those are bounds on how fast you could execute. Did I have a question in the back there? No. Okay. So let's see what happens to work and span in terms of how we can understand our programs and decompose them. So suppose that I have a computation A followed by a computation B, and I connect them in series. What happens to the work? How does the work of this whole thing correspond to the work of A and the work of B? What's that? Yeah, just add them together. Okay? You get T1 of A plus T1 of B. Take the work of this and the work of this. Okay? That's pretty easy. Okay, what about the span? So the span is the longest path of dependencies. What happens to the span when I connect two things in series? Yeah, it just sums as well. Okay, because I take whatever the longest path is from here to here, and then the longest one from here to here, just adds. Okay, but now let's look at parallel composition. So now suppose that I can execute these two things in parallel. What happens to the work? Yeah, it just adds, okay, just as before. So the work always adds. The work is easy because it's additive, okay? What happens to the span? What's that? It's the max of the spans. Right. So whatever is the longest, whichever one of these ones has a longer span, that's going to be the span of the total. Does that give you some intuition? So we're going to see when we analyze the spans of things that in fact, we're going to see maxes occurring all over the place. Okay. So speedup is defined to be T1 over TP. Okay? So speedup is how much faster am I on P processors than I am on one processor. Okay? Pretty easy. So if T1 over TP is equal to P, we say we have perfect linear speedup, or a linear speedup. Okay? If we're getting, that's good, right? Because if I put on, use P processors, I'd like to have things go P times faster. Okay? That would be the ideal world. Okay. If T1 over TP, which is the speedup, is greater than P, that says we have superlinear speedup. And in our model, we don't get that because of the work law. Because the work law says TP is greater than or equal to T1 over P. And just do a little algebra here, you get T1 over TP must be less than or equal to P. Okay? So you can't get superlinear speedup. In practice, there are situations where you can get superlinear speedup due to caching effects and a variety of things. We'll talk about some of those things. But in this simple model, we don't get that, that kind of behavior. Okay? Of course, the case I left out is the common case, which is that T1 over TP is less than P. Okay? And that's very common that people write code which doesn't give them linear speedup. Okay? But we're mostly interested in getting linear speedup here. That's our goal. Okay? So that we're getting the most bang for the buck out of the processors we're using. Okay, parallelism. So we're finally to the point where I can talk about parallelism and give a quantitative definition of parallelism. Okay, so the span law says that TP is at least T infinity, right? The time on P processors is at least the time on infinite number of processors. So the maximum possible speedup, that's T1 over TP, given T1 and T infinity is T1 over T infinity. Okay? And we call that the parallelism. Okay? It's the maximum amount of speedup we could possibly attain. Okay? So we have the speedup, and the speedup by the span law, it says this is the maximum amount we can get. We can also view it as if I look along the critical path of the computation, Okay, it's sort of what's the average amount of work at every level. So work, the total amount of stuff here, divided by that length there. That sort of tells us the width, what's the average amount of stuff that's going on at every step. Okay? So for this example, what is the, I forgot to put this on my slide. For this example, what is the parallelism of this particular DAG here? Two, right? So the span has length 9. This is assuming everything was unit time. Obviously, in reality, when you have more instructions, you in fact, would make it be whatever the length of this was in terms of number of instructions or what have you, okay, of execution time of all these things. So this is length 9. There's 18 things here. Parallelism is 2. Okay, so we can quantify parallelism precisely, and we'll see why it's important to quantify that. So that's the maximum speed up we're going to get when we run this application. Okay, here's another example that we did before, fib of 4. Okay, so let's assume again that each strand takes unit time to execute. Okay, so what is the work in this particular computation? Assume every strand takes unit time to execute, which of course it doesn't, but. Anybody care to hazard a guess? 17, yeah, because there's 4 nodes here that have 3 plus 5. So 3 times 4 plus 5 is 17. Okay? So the work is 17. Okay, what's the span? This one's tricky. Too bad it's not a little bit more focused, but. What's the span? 8. That's correct. Who got 7? Yeah, so I got 7 when I did this, and then I looked harder and it was 8. Okay, it's 8. So here it is. Let's see here. Here's the span. There it goes. Ooh, that little side step there, that's what makes it 8. Okay, so basically it comes down here, and I had gone down like that when I did it. But in fact, you got to go over and back up. So it's actually 8. Okay? So that says that the parallelism is a little bit more than 2, 2 1/8. Okay? What that says is that if I use many more than 2 processors, I can't get linear speed up anymore. I'm only going to get marginal performance gains. Okay? If I use more than 2 processors, because the maximum speed up I can get is like 2.125 if I had an infinite number of processors. Okay? So any questions about this? So this is, by the way, this is deceptively simple, and yet if you don't play around with it a little bit, you can get confused very easily. Okay? Deceptively simple, but very powerful. Okay, to be able to do this. Okay, so here we have, so for the analysis of parallelism, one of the things that we have going for us in using the Silk tool suite is a program called Silkview, which has a scalability analyzer. And it is like the race detector that I talked to you about last time in that it uses dynamic instrumentation. So you run it under Silkview, your program under Silkview. It's like running it under Valgrind, for example, or what have you. So basically you run your program under it and it analyzes your program for scalability. Okay? It computes the work and span of your program to derive some upper bounds on parallel performance. And it also estimates a scheduling overhead to compute what's called a burden span for lower bounds. Okay? So let's take a look. So here's, for example, here's a quick sort program. So let's just see what this is a C++ program. So here we're using a template so that the type of items that I'm sorting I can make be a variable. Okay, so type name. Can we shut the back door there? One of the TAs, somebody run up to. Thank you. So we have a variable t, and we're going to quick sort from the beginning to the end of the array. And what we do is, just as you're familiar with quicksort, if there's actually something to be sorted, more than one thing, then we find the middle by partitioning the thing. And this is a bit of C++ magic to find the middle element. And then the important part from our point of view is after we've done this partition, we quicksort the first part of the array from beginning to middle, and then from the beginning plus 1 of the middle, whichever, begin plus 1 or the middle, whichever is greater, to the end. And then we sync. So what we're doing is quicksort where we're spawning off the two subproblems to be solved in parallel recursively. So they're going to execute in parallel, and they're going to execute in parallel, and so forth. Okay? So a fairly natural thing to do divide and conquer on quicksort, because the two subproblems can be operated on independently. So we just sort them recursively, but we can sort them in parallel. Okay, so suppose that we're sorting 100,000 numbers. How much parallelism do you think is in this code? So remember that we're getting this recursive stuff done. How many people think, well, it's not going to be more than 100,000, I promise you. So how many people think more than 1 million parallelism? Raise your hand, more than 1 million. Okay, and how many people think more than 100,000? And how many people think more than 10,000? Okay, between the two, right? Anybody? Okay, more than 1,000? Okay, 1,000, okay. How about more than 100? 100 to 1,000. How about 10 to 100? How about between 1 and 10? Okay. So a lot of people think between 1 and 10. Why do you think that there's so little parallelism in this? You don't have to justify yourself. Okay. Well, let's see how much there is according to Silkview. So here's the type of output that you'll get. You get a graphical curve. You also get a textual output, but this is sort of the graphical output. And this is basically, it's showing what the running time here is. So the first thing it shows is it will actually run your program, benchmark your program on, in this case, up to 8 cores. We ran it, okay? So we ran it up to 8 cores and give you what your measured speedup is, okay? So the second thing is it tells you the parallelism. If you can't read that, it's 11.21. Okay, so we get about 11. Why do you think it's not higher? What's that?
It's the log.
What's the log?
Every time you spawn a thread, you only do that for half of the original size. So
Yeah, but you're doing the two things in parallel, right? We'll actually analyze this. So it has to do with the fact that the partition routine is a serial piece of code, and it's big. So the initial partitioning takes you 100 million steps of doing a partition, okay, before you get to do any parallelism at all. Okay, we'll see that in just a minute. Okay, so it gives you the parallelism. It also plots this, okay? So this is the parallelism. Notice that's the same number. 11.21 is plotted as this bound. Okay, so it tells you the span law. And it tells you the work law. This is the linear speedup. If you were having linear speedup, this is what your program would give you. So it gives you these two bounds, the work law and the span law, on your speedup. And then it also computes what's called a burden parallelism, estimating scheduling overheads to sort of give you a lower bound. Now, that's not to say that your numbers can't fall outside this range. But when they do, it will tell you essentially what the issues are with your program. Okay, and we'll discuss how you diagnose some of those issues. Actually, that's in one of the handouts that we've provided. I think that's in one of the handouts. If not, we'll make sure it's in one of the handouts. Okay. Okay, so it basically gives you a range for what you can expect. So the important thing here is to notice here, for example, that we're losing performance, but it's not due to the parallelism, to the work law, or the basically, in some sense, what's happening is we are losing it because of the span law, because we're starting to approach the point where the span is going to be the issue. So we'll talk more about this. So the main thing is you have a tool that can tell you the work and span, and so that you can analyze your own programs to understand, are you bounded by parallelism, for example, in particular, in the code that you've written. Okay, let's do, though, a theoretical analysis of this to understand why that number is small. Okay, so the main thing here is that the expected work, as you recall, of quicksort is order n log n. Right? You tend to do order n log n work. You partition, and then you're solving two problems of the same size. If you actually draw out the recursion tree, it's log height with linear amount of work on every level for n log n total work. Okay. The expected span, however, is order n, because the partition routine is a serial program that partitions up the thing of size n in order n time. So when you compute the parallelism, you get parallelism as of order log n, and log n is kind of puny parallelism. That's our technical word for it. Okay, so puny parallelism is what we get out of quicksort. It turns out there are lots of things that you can analyze. Here's just a selection of some of the interesting practical algorithms and the kinds of analyses that you can do, showing that, for example, with merge sort, you can do it with work n log n. You can get a span of log cubed n, and so then the parallelism is the ratio of the two. Okay, and in fact, you can actually theoretically get log squared n span, but that's not as practical an algorithm as the one that gives you log cubed n. And you can go through, and there are a whole bunch of algorithms for which you can get very good parallelism. So all of these, if you look at the ratio of these, the parallelism is quite high. So let's talk a little bit about what's going on underneath and why parallelism is important. Okay? So when you describe your program in Silk, you express the potential parallelism of your application. Okay? You don't say exactly how it's going to be scheduled. That's done by the SoPlus Scheduler, which maps the strands dynamically onto the processors at runtime. Okay? So it's going to do the load balancing and everything necessary to balance your computation off the number of processors. We want to understand how that process works, because that's going to help us to understand how it is that we can build codes that will map very effectively onto the number of processors. Now, it turns out that the theory of the distributed scheduler, such as is in SoPlus, is complicated. I'll wave my hands about it towards the end, but the analysis of it is advanced. You have to take a graduate course to get that stuff. Okay? So instead, we're going to explore the ideas with a centralized, much simpler scheduler, okay, which serves as a surrogate for understanding what's going on. Okay? So the basic idea of almost all scheduling theory in this domain is greedy scheduling. Okay? And so this is, by the way, we're coming to the second thing that you have to understand really well in order to be able to generate good code, the second sort of theoretical thing. So the idea of a greedy scheduler is you want to do as much work as possible on each step. Okay? So the idea here is let's take a look, for example. Suppose that we've executed this part of the DAG already. Okay? Then there are a certain number of strands that are ready to execute. Okay? Meaning all their predecessors have executed. How many strands are ready to execute on this DAG? 5. Okay, right? These guys. Okay, so those 5 strands are ready to execute. So the idea is, and let me illustrate for p equals 3, the idea is to understand the execution in terms of two types of steps. So in a greedy schedule, you always do as much as possible. So this is what would be called a complete step, because I can schedule all 3 processors to have some work to do on that step. Okay? So which are the best 3 guys to be able to execute? Yeah, so I'm not sure what the best 3 are, but for sure you want to get this guy and this guy, right? Maybe that guy's not as, but this guy you definitely want to execute, right? And these guys, I guess, are okay, but you definitely want to get. So in a greedy schedule, no, you're not allowed to look to see which ones are the best to execute. You don't know what the future is. The scheduler isn't going to know what the future is. So it just executes any P cores. You just execute any P cores. In this case, I executed those P strands. In this case, I executed these 3 guys, even though they weren't necessarily the best. And in a greedy scheduler, it doesn't look to see what's the best one to execute. It just executes as many as it can. In this case, it's P. Now we have what's called an incomplete step. Notice nothing got enabled. That was sort of too bad. Okay, so there's only 2 guys that are ready to go. What do you think happens if I have an incomplete step, namely P strands are ready, fewer than P strands are ready? I just execute all of them. Okay, as many as I can, run all of them. So that's what a greedy scheduler does. It's just on every step, it executes as many as it can. And we can classify the steps as ones which are complete, meaning we used all our processors, versus incomplete, meaning we only used a subset of our processors in scheduling it. Okay? So that's what a greedy scheduler does. Now the important thing, okay, which is the analysis of this program. Okay? And this is, by the way, the single most important thing in scheduling theory that you're going to ever learn. Okay? Is this particular theorem. It goes all the way back to 1968. And what it basically says is any greedy scheduler achieves a bound of T1 over P plus T infinity. So why is that an interesting upper bound? Yeah?
Because that says that, I mean, it's kind of a refinement of what you said before. Like, even if you add as many processors that you can, basically you're bounded by that T infinity.
Yeah.
And even you have like a T, like, it would also relate to work. Basically, we're kind of telling you.
Yeah, so basically each of these, this term here is the term in the work law. This is the term in the span law. And we're saying you can always achieve the sum of those 2 lower bounds as an upper bound. Okay, so let's see how we do this, and then we'll look at some of the implications. Question? Did you have a question? No. Okay. So here's the proof that you meet this. So the proof says, okay, and I'll illustrate for p equals 3. How many complete steps could we have? So I argue that the number of complete steps is at most T1 over P. Why is that? Well, every complete step performs P work. So if I had more complete steps than T1 over P, I'd be doing more than T1 work. But I only have T1 work to do. Okay, so the maximum number of complete steps I could have is at most T1 over P. People follow that? Okay. So the trickier part of the proof, which is not all that tricky, but is a little bit trickier, is the other side. How many incomplete steps could I have? So we execute those. So I claim that the number of incomplete steps is bounded by the critical path length, by the span. Okay, why is that? Well, let's take a look at the part of the DAG that has yet to be executed. Okay, so that this gray part here. There's some span associated with that. In this case, it's this longest path. Well, when I execute all of the ready threads that are ready to go, I guarantee to reduce the span of that unexecuted DAG by at least 1. Okay? So as I do here. So I reduce it by 1 when I execute. So if I have a complete step, I don't guarantee to reduce the span of the unexecuted DAG. Because I may execute things, as I showed you in this example, where you don't actually advance anything. But I execute all the ready threads, okay, on an incomplete step. And that's going to reduce it by 1. So the number of incomplete steps is at most t infinity. So the total number of steps is at most the sum. So as I say, this proof you should understand in your sleep, because it's the most important scheduling theory proof that you're going to probably see in your lifetime. Okay? It's very old and really very, very simple, and yet there's a huge amount of scheduling theory, if you ever look at scheduling theory, that comes out of this, just making this same problem more complicated and more real and more interesting and so forth. Okay, but this is really the crux of what's going on. Okay, any questions about this proof? So one corollary of the greedy scheduling algorithm is that any greedy scheduler achieves within a factor of 2 of optimal scheduling. Okay, so let's see why that is. So it's guaranteed as an upper bound to get within a factor of 2 of optimal. So here's the proof. So let's let TP star be the execution time produced by the optimal scheduler. This is the scheduler that knows the whole DAG in advance and can schedule things exactly where they need to be scheduled to minimize the total amount of time. Now, even though the optimal scheduler can schedule very efficiently, it's still bound by the work law and the span law. Okay? So therefore, TP star is still got to be greater than T1 over P and greater than T infinity by the work and span laws. Even though it's optimal, it still has, every scheduler must obey the work law and span law. Okay? So then we have, by the greedy scheduling theorem, TP is at most T1 over P plus T infinity. Well, that's at most twice the maximum of these two values. Whichever is larger, I've just plugged in to get the maximum of those two. And that's at most, by this equation, twice the optimal time. Okay? So this is a very simple corollary. Says, oh, greedy scheduling is actually pretty good. It's not optimal. In fact, optimal scheduling is NP complete. Very hard problem to solve. But getting within a factor of 2, you just do greedy scheduling. It works fine. Okay? More importantly is the next corollary, which has to do with when do you get linear speedup. And this is, I think, the most important thing to get out of this. So any greedy scheduler achieves near perfect linear speedup whenever, what's this thing on the left-hand side? What's the name we called that? The parallelism, right? That's the parallelism, is much bigger than the number of processors you're running on. So if the number of processors you're running on is smaller than the parallelism of your code, it says you can expect near perfect linear speedup. Okay, so what does that say you want to do in your program? You want to make sure you have ample parallelism. And then the scheduler will be able to schedule it so that you get near perfect linear speedup. Let's see why that's true. Okay, so T1 over T infinity is much bigger than P is equivalent to saying that T infinity is much less than T1 over P. Okay, that's just algebra. Okay, well, what does that mean? The greedy scheduling theorem says TP is at most T1 over P plus T infinity. We just said that if we have this condition, then T infinity is very small compared to T1 over P. So if this is negligible, then the whole thing is about T1 over P. Okay? Well, that just says that the speedup is about P. Okay? So the name of the game is to make sure that your span is relatively short compared to the amount of work per processor that you're doing. Okay? And in that case, you'll get linear speedup. Okay? And that happens when you've got enough parallelism compared to the number of processors you're running on. Any questions about this? This is like the most important thing you're going to learn about parallel computing. Okay? Everything else we're going to do is going to be derivatives of this. So if you don't understand this, you're going to have a hard time with the other stuff. Okay? So it's in some sense, it's deceptively simple, right? We just have a few variables, T1, TP, T infinity, P. There's not much else going on, but there are these bounds, okay, and these elegant theorems that tell us something about how no matter what the shape of the DAG is or whatever, these two values, the work and the span, really characterize to very closely, where it is that you can expect to get linear speedup. Okay, any questions? Okay. Good. Okay, so the quantity T1 over PT infinity, so what is that? That's just the parallelism divided by P. That's called the parallel slackness. Okay, so this parallel slackness is 10, means you're running on 10 times more, you have 10 times more parallelism than processors. So if you have high slackness, you can expect to get linear speedup. If you have low slackness, don't expect to get linear speedup. Okay, now the scheduler we're using is not a greedy scheduler. Okay, it's better. Okay, in many ways, because it's a distributed, what's called work-stealing scheduler, and I'll show you how it works in a little bit. But it's based on the same theory. Okay, even though it's a more complicated scheduler from a analytical point of view, it's really based on the same theory as greedy scheduling. It guarantees that the time on P processors is at most T1 over P plus order T infinity. So there's a constant here. Okay, and it's a randomized scheduler. So it actually only guarantees this in expectation. It actually guarantees this very close to this with high probability. Okay, so the difference is the big O. But if you look at any of the formulas that we did with the greedy scheduler, the fact that there's a constant there doesn't really matter. You get the same effect. It just means that the slackness that you need to get linear speedup has to not only overcome the T infinity, it's also got to overcome the constant there. Okay? And empirically, it actually turns out this is not bad as an estimate using the greedy bound. Okay? Not bad as an estimate. And so this is sort of the model that we'll take, is sort of as if we're doing things with a greedy scheduler. Okay? And that'll be very close for what we're actually going to see in practice with the SoPlus scheduler. So once again, it means near perfect linear speedup as long as P is much less than T1 over T infinity, generally. And so Silkview allows us to measure T1 and T infinity, right? So that's going to be good, because then we can figure out what our parallelism is and look to see, we're running on typically 12 cores. How much parallelism do we have? Okay, if our parallelism is 12, we don't have a lot of slackness. We won't get very good speedup. But if we have a parallelism of, say, 10 times more, let's say 120, we should get very, very good parallelism, very, very good speedup on 12 cores. We should get close to perfect speedup. Okay? Okay, so let's talk about the runtime system and how this work-stealing scheduler works, and because it's different from the other one. And this will be helpful also for understanding how it is that you're, when you program these things, what you can expect. So the basic idea of the scheduler is, so there's two strategies that people have explored for doing scheduling. One is called work sharing, which is not what SoPlus does, but let me explain what work sharing is, because it's helpful to contrast it with work stealing. So in work sharing, what you do is when you spawn off some work, you say, let me go find some low utilized processor and put that work there for it to operate on. Okay? And the problem with work sharing is that you have to do some communication and synchronization every time you do a spawn. Okay, every time you do a spawn, you're going to go out. This is kind of what pthreads does when you do pthread create. It goes out and it says, okay, let me create all of the things it needs to do and get it scheduled on then on a processor. Okay. Work stealing, on the other hand, takes the opposite approach. Whenever it spawns work, it just is going to keep that work local to it, but make it available for stealing. A processor that runs out of work then is going to go looking for work to steal, to bring back. And the advantage of work stealing is that the processor doesn't do any synchronization except when it's actually load balancing. So if all the processors have ample work to do, okay, if all the processors have ample work to do, then what happens is there's no overhead for scheduling whatsoever. They all just crank away, okay? And so you get very, very low overheads when there's ample work to do on each processor. So let's see how this works. So the particular way that it maintains it is that basically each processor maintains a work deck. So a deck is a double-ended queue, okay, and of the ready strands. And it manipulates the bottom of the deck like a stack. So what that says is, for example, here we had a spawn followed by 2 calls, okay? And basically it's operating it just as it would operate an ordinary stack. So here we go, ordinary call stack. So if, for example, this guy says call, well, it pushes a frame on the bottom of the call stack, just like normal. Okay? If it says spawn, it pushes a spawn frame on the bottom of the deck. Okay? Okay, in fact, of course, it's running in parallel, so you can have a bunch of guys that are both calling and spawning, and they all push whatever their frames are. When somebody says return, you just pop it off. Okay? So in the common case, each of these guys is just executing the code serially the way that it would normally execute in C or C++. Okay? However, if somebody runs out of work, then it becomes a thief. And it looks for a victim. And the strategy that's used by Silk++ is to look at random. It says, let me just go to any other thread and any other, processor, any other the workers, I call these workers, okay? Any of those workers and grab away some of their work. But when it grabs it away, what it does is it steals it from the opposite end of the deck from where this particular victim is actually doing its work. So it steals the oldest stuff first. Okay, so it moves that over. And now here what it's doing is it's stealing up to the point that is spawned. So it steals from the top of the deck down to where there's a spawn on top. Yes?
Is there always a spawn on the top of every deck?
Close. Almost always. Yes. And so I think that you could say that so the initial deck does not have a spawn on top of it, but you could imagine that it did. And then when you steal, you're always stealing from the top down to a spawn. If there isn't something, if this is just a call here, this cannot any longer be stolen. There's no work there to be stolen because this is just a single execution. There's nothing that's been spawned off at this point. Okay, this is the result of having been spawned as opposed to that it's doing a spawn. So yes, basically you're right. There's a spawn on the top. So it basically steals that off, and then it resumes execution, okay, afterwards, and it starts then operating just like an ordinary deck. So the theorem that you can prove for this type of scheduler is that if you have sufficient parallelism, okay, so you all know what parallelism is at this point, okay, you can prove that the workers steal infrequently. Okay, so in a typical execution, you might have a few hundred load balancing operations of this nature for something which is doing, billions and billions of instructions. Okay, so you steal infrequently. If you're stealing infrequently and all the rest of the time you're just executing like the C or C++, hey, now you've got linear speedup because you've got all of these guys working all the time. Okay? And so, as I say, so the main thing to understand is that there's this work-stealing scheduler running underneath. It's more complicated to analyze than the greedy scheduler, but it gives you pretty much the same, qualitative kinds of results. Okay? And the idea then is that you want to, that the stealing occurs infrequently, so you get linear speedup. So the idea then is, just as with greedy scheduling, make sure you have enough parallelism, because then the load balancing is a small fraction of the time these processors are spending executing the code. Okay? Because whenever it's doing things like work stealing, it's not working on your code, executing, making it go fast. Okay? It's doing bookkeeping and overhead and stuff. So you want to make sure that stays low. So any questions about that? So specifically, we have these bounds. Okay? It achieves this expected running time, which I mentioned before. Let me give you a pseudo proof of this. Okay? So this is not a real proof because it ignores things like independence of probabilities. Okay? So when you do a probability analysis, you're not allowed to multiply probabilities unless they're independent. So anyway, here I'm multiplying probabilities that are independent. So the idea is you can view a processor as either working or stealing. So it goes into one of two modes. Okay, it's going to be stealing if it's run out of work. Okay, otherwise it's working. So the total time all processors spend working is T1. Hooray, that's at least a bound. Now it turns out that every steal has a 1 over p chance of reducing the span by 1. So you can prove that of all of the work that's in the top of all those decks, that those are where any of the ready threads are going to be that are in a position of reducing the span if you execute them. And so whenever you steal, you have a 1 over p chance of hitting the guy that matters for the span of the unexecuted DAG. So same kind of thing as in theory. Okay, so you have a 1 over p chance. So the expected cost of all steals is order pt infinity. Okay, so this is true, but not for this reason. Okay, but it's kind of, the intuition is right. Okay, so therefore the cost of all steals is pt infinity, and the cost of the work is t1. So that's the total amount of work and time spent stealing by all the p processors. So to get the time spent doing that, we divide by p, because they're p processors. Okay? And when I do that, I get t1 over p plus order t infinity. So that's kind of where that bound is coming from. So you can see what's important here is that the term, the order t infinity term, this is the one where all the overhead of scheduling and synchronization is. There's no overhead for scheduling and synchronization in the t1 over p term. The only overhead there is to do things like mark the frames as being a steal frame or a spawn frame, so that, and do the bookkeeping of the deck as you're executing, so that a spawn can be implemented very cheaply. Now, in addition to the scheduling things, there's some other things to understand a little bit about the scheduler, and that is that it supports the C++ rule for pointers. So remember in C and C++ that you can pass a pointer to stack space down, but you can't pass a pointer to stack space back to your parent, right? Because it gets popped off, okay? So if you think about a C or C++ execution, let's say we have this call structure here, okay? A really cannot see any of the stack space of B, C, D, or E. So this is what A gets to see. And B, meanwhile, can see A space, because that's down on the stack, but it can't see C, D, or E. Particularly if you're executing this serially, it can't see C, because C hasn't executed yet when B executes. However, C, it turns out, the same thing is I can't see any of the variables that might be allocated in the space for B when I'm executing here on the stack, Okay, you can see them in the heap, but not on the stack, because B has been popped off at that point, and so forth. So this is basically the normal rule, the normal views of stack that you get in C or C++. In Silk++, you get exactly the same behavior, okay, except that multiple ones of these views may exist at the same time. So if, for example, B and C are both executing at the same time, they each will see their own stack space and a stack space, okay? And so the cactus stack maintains that fiction that you can sort of look at your ancestors and see your ancestors, but now it's maintained, it's called a cactus stack because it's kind of like a tree structure, okay? Upside down, like a, what's the name of that big cactus out west? Yeah, saguaro cactus, yep. Okay, this kind of looks like that if you look at the stacks. This leads to a very powerful bound on how much space your program is using. So normally if you do a greedy scheduler, you could end up using gobs more space than you would in a serial execution, gobs more stack space. Okay? In Silk++ programs, you have a bound. It's P times S1 is the maximum amount of stack space that you'll ever use, where S1 is the stack space used by a serial execution. So if you can keep your serial execution to use a reasonable amount of stack space, and usually it does, then in parallel you don't use more than P times that amount of stack space. And the proof for that is sort of by induction, which is basically says there's a property called the busy leaves algorithm, busy leaves property, excuse me, that says that if you have a leaf that that's being worked on but hasn't been completed, okay, so I've indicated those by the purple and pink ones, then if it's a leaf, it has a worker executing on it. And so therefore, if you look at how much stack space you're using, each of these guys can trace up, and they may double count the stack space, but it'll still be bounded by P times the depth that they're at, or P times S1, which is the maximum amount. Okay, so it has good space bounds. That's not so crucial for you folks to know as a practical matter, but it would be if this didn't hold. Okay, if this didn't hold, then you would have more programming problems than you'll have. The implications of this work-stealing scheduler is interesting from the linguistic point of view, because you can write a code like this. So for I gets 1 to a billion, okay, spawn some subroutine foo of I, and then sync. So one way of executing this, the way that the work sharing schedulers tend to do this, is they say, oh, I've got a billion tasks to do. So let me create a billion tasks and now schedule them. And the space just, boom, to store all those billion tasks gets to be huge. Now, of course, they have some strategy they can use to reduce it by bunching tasks together and so forth. But in principle, you've got a billion pieces of work to do, even if you execute on one processor. Okay? Whereas in the work-stealing type execution, what happens is you execute this, in fact, depth first search. So basically, you're going to execute foo of 1, and then you'll return. And then you'll increment I, and you'll execute foo of 2, and you'll return. And at no time are you using more than, in this case, 2 stack frames, one for this routine here and one for foo, because you basically keep going up, because you're using your stack on demand rather than creating all the work up front to be scheduled. Okay? So the work-stealing scheduler is very good from that point of view. The tricky thing for people to understand is that if you're executing on multiple processors, when you do silk spawn, the processor, the worker that you're running on, is going to execute foo of 1. The next statement, which would basically be incrementing the counter and so forth, the next statement is executed by whatever processor comes in and steals that continuation. Okay? So if you had 2 processors, they're each going to basically be executing. The first processor isn't the one that executes everything in this function. This function has its execution shared. The strands are going to be shared where the first part of it would be done by processor 1 and the latter part of it would be done by processor 2. And then when processor 1 finishes this off, it might go back and steal back from processor 2. Okay? So the important thing there is it's generating its stack needs sort of on demand rather than all up front. And that keeps the amount of stack space small as it executes. So the moral is it's better to steal your parents from their children than stealing children from their parents. Okay. Okay. So that's the advantage of doing this sort of parent stealing, because you're always stealing the frame, which is an ancestor of where that worker is working. And that means resuming a function right in the middle on a different processor. That's kind of the magic of the technology, is how do you actually move a stack frame from one place to another and resume it in the middle. Okay, let's finish up here with a chess lesson. Okay, promised a chess lesson, so we might as well do some fun and games. We have a lot of experience at MIT with chess programs. We've had a lot of success. Probably our closest one was Socrates 2.0, which took second place in the World Computer Chess Championship, running on an 1824 node Intel Paragon, so a big supercomputer. Okay, running with the Silk Scheduler. We actually almost won that competition, and it's a sad story that maybe sometime around dinner or something can tell you the sad story behind it, but I'm not going to tell you for why we didn't take first place. Okay, and we've had a bunch of other successes over the years. Okay, right now our chess programming is dormant. We're not doing that in my group anymore, but in the past, we had some very strong chess playing programs. So what we did was with Star Socrates, which was one of our programs, was we wanted to understand the Silk Scheduler. And so what we did is we ran a whole bunch of different positions on different numbers of processors, and which ran for different amounts of time. Okay? We wanted to plot them all on the same chart. Okay, and here's our strategy for doing it. What we decided to do was do a standard speedup curve. So a standard speedup curve says, let's plot the number of processors along this axis and the speedup along that axis. Okay? But in order to fit all these things on the same processor curve, what we did was we normalized the speedup. So what's the maximum so here's the speedup. So if you look at the numerator here, this is the speedup, T1 over TP. What we did is we normalized it by the parallelism. So we said, what fraction of perfect speedup can we get? Okay? So here 1 says that I got exactly speedup of, this is the maximum possible speedup that I can get, because the maximum possible value of T1 over P is T1 over T infinity. Okay? So that's sort of the maximum. Okay? On this axis, we said how many processors you're running on it. Well, we looked at that relative to essentially the slackness. So notice by normalizing, we essentially have here the inverse of the slackness. So 1 here says that I'm running on exactly the same number of processors as my parallelism. A 10th here says that I've got a slackness of 10. Okay, I'm running on 10 times fewer processors than parallelism. Okay, out here I'm saying I got way more processors than I have parallelism. Okay, so I plotted all the points. So you can, it doesn't show up very well here, but all those green points, there are a lot of green points here, that's our performance. Okay, measured performance. Okay, so you can sort of see they're green there. Not the best color for this projector. Okay? So we plotted on this essentially the work law and the span law. So this is the work law, it says linear speedup, and this is the span law. And you can see that we're getting very close to perfect linear speedup as long as our slackness is 10 or greater. Okay, you see that? It's hugging that curve really tightly. As we approach a slackness of 1, okay, you can see that we start to get, it starts to go away from the linear speedup curve. Okay? So for this program, if you look, it says, gee, if we were running with 10 times a slackness of 10 times more parallelism than processors, we're getting almost perfect linear speedup in the number of processors we're running on across a wide range of number of processors, wide range of benchmarks for this chess program. And in fact, this curve is the curve. This is not an interpolation here, but rather there's just the greedy scheduling curve. And you can see it does a pretty good job of going through all the points here. Greedy scheduling does a pretty good job of predicting the performance. The other thing you should notice is that although things are very tight down here, as you approach up here, they start getting more spread. And the reason is that as you start having more of the span mattering in the calculation, you also have, that's where all the synchronization, communication, all of the overhead of actually doing the mechanics of moving a frame from one processor to another take into account. And so you get a lot more spread as you go up here. Okay? So that's just the first part of the lesson. The first part was, oh, you know, we actually, if you have, you know, the theory works out in practice, okay, for real programs. If you have like 10 times more processors, sorry, 10 times more parallelism than processors, you're going to do a pretty good job of getting linear speedup. Okay, so that says you guys should be shooting for parallelisms on the order of 100, okay, for running on 12 cores. Somewhere in that vicinity, you should be doing pretty well if you've got parallelism of 100 when you measure it for your codes. Okay, so yeah, so we normalize by the parallelism there. Okay, now, the real lesson, though, was understanding how to use things like work and span to make decisions in the design of our program. So as it turned out that Socrates, for this particular competition, was to run on a 512 processor connection machine at the University of Illinois. So this was in the early 1990s. It was one of the most powerful machines in the world, and this thing is probably more powerful, you know, today. Okay, but in those days it was a pretty powerful machine. I don't know whether this thing is, but this thing probably, I'm pretty sure, is more powerful. So this was a big machine. However, here at MIT, we didn't have a great big machine like that. Okay, we only had a 32 processor CM5. Okay, so we were developing on a little machine, expecting to run on a big machine. Okay, so one of the developers proposed a change to the program that produced a speedup of over 20% on the MIT machine. Okay, so we said, oh, that's pretty good, 25% improvement. But we did a back-of-the-envelope calculation and rejected that improvement because we were able to use work and span to predict the behavior on the big machine. Okay, so let's see how that worked out, why that worked out. So I've fudged these numbers so that they're easy to do the math on and easy to understand, okay? The real numbers actually, though, did sort out very, very similar to what I'm saying, just they weren't round numbers like I'm going to give you, okay? So the original program ran for, let's say, 65 seconds on 32 cores. The proposed program ran for 40 seconds on 32 cores. Sounds like a good improvement to me. Let's go for the faster program. Well, let's hold your horses, okay? Let's take a look at our performance model based on greedy scheduling, okay? That TP is T1 over P plus T infinity. What component, we really need to understand to scale this, what component of each of these things is work and which is span, because that's how we're going to be able to predict what's going to happen on a big machine. So indeed, this original program had a work of 2,048 seconds, okay, and a span of 1 second. Now this is, chess, it turns out, is a non-deterministic type of program where you use speculative parallelism, okay, which is, and so in order to get more parallelism, you can sacrifice, you know, and do more work versus less work. So this one had over here, that we improved it to, had less work on the benchmark, but it had a longer span, okay? So it had less work but a longer span. So when we actually were going to run this on the 500, well, first of all, we did the calculation. It actually came out pretty close. I was kind of surprised how close the theory matched. We actually, on 32 processors, if you do the work span calculation, you get that it's 65 seconds on our 32 processor machine. Here we had 40 seconds. Okay? But now what happens when we scale this to the big machine? Okay? So here we scaled it to 512 cores. So now we take the work divided by the number of processors, 512 plus 1. That's 5 seconds for this. Here we have the work, but we now have a much larger span. So we have 2 seconds of work per processor, but now 8 seconds of span for a total of 10 seconds. So had we made this, quote, improvement, our code would have been half as fast. Okay? It would not have scaled. Okay? And so the point is that work and span typically will beat running times for predicting scalability of performance. So you can measure a particular thing, but what you really want to know is this going to scale? And how is it going to scale into the future? So people who are building multi-core applications today want to know that they code it up. They don't want to be told in 2 years they've got to recode it all because the number of cores doubled. Okay? They want to have some future-proof notion that, hey, there's a lot of parallelism in this program. Okay? So work and span, eat it, drink it, sleep it, work and span, work and span, work and span. Okay, work and span, work and span. Okay, work and span.